Starting off Chapter 3, we're going to learn about solving systems using tables and graphs. A system of equations is two or more equations. A solution is the point that makes all the equations true. And I want to emphasize all of the equations. The first method is using a table or a graph to solve. If we're going to solve by graphing, then the first thing we need to do is solve both sides for y. That way it's in slope-intercept form. Then we can graph the equation, find the intersecting point, and finish off by writing our answer as an ordered pair. Here we have the two equations in our system. First thing we're going to do is solve both of them for y. So we had 5x plus 10y equals 20. We can subtract 5x to both sides, so 10y equals negative 5x plus 20. Divide everything by 10, and y will equal negative 1/2 x plus 2. We can do the same thing with the second equation, x plus 3y equals 9. Subtract x to both sides, and 3y equals negative x plus 9. Divide everything by 3, and y equals negative 1/3 x plus 3. Then we're ready for step number 2, which says graph both equations. The first one, our y-intercept is at positive 2, with a slope of negative 1/2, so down 1 and over 2. Same thing, we could go up and over 2 to the left instead. Now, it is going to be important that you graph your line straight, so if you only put 2 points, make sure that you use a ruler to get straight lines. Otherwise, plot extra points so you can get straight lines. And here is our first line. Same thing with the other one, we start at positive 3, but now we have a slope of negative 1/3, so down 1 and over 3, and up 1 and over 3 in the opposite direction. And we can connect these points. Now, for our third step, we want to find where our intersection point is, which is right here. Last step for number 4 is we want to write it as an ordered pair. Remember, the x value comes first, so that'll be negative 6, followed by the y value of 5. And that is the solution to our system. Let's do a quick check to make sure that both of these points work. We can check by plugging them back into the original equations. So we had 5x plus 10y equals 20. We can do 5 times negative 6 plus 10 times 5, just plugging in the points from our solution and see if it works. We'll have negative 30 plus 50 equals 20, and sure enough, 20 equals 20. We need to check with the other equation though too, which was x plus 3y equals 9. Again, we'll replace the x with negative 6, we'll replace the y with 5, and see if it works out. Negative 6 plus 15, sure in fact, is 9, so this solution also works. This means whenever you're solving a system of equations, you can always know if your answer is correct by plugging the ordered pair back into the original equations. Another way to solve is by using a table. You want to solve both equations for y, then we'll use our calculators to do steps 2 and 3. On step 4, we're going to find where y1 equals y2, and then we can write our answer as an ordered pair. To use a table to solve a system of equations, we're going to go into y equals. Then we're going to type in the same equations we just did when we were graphing them. We'll have negative 1/2 x plus 2 for the first equation, go down to y2 for the second one, which was negative 1/3 x plus 3. Then we can press the second and the graph button, which really takes us to the table. Next, we need to scroll through our table to find where the y1 values are equal to the y2 values. We can go down this way, and as we go down this way, we'll notice that the y1 values are getting further away from the y2 values. So let's go into the opposite direction. Once you start scrolling in the negative direction, we're going to find that when x is negative 6, both the y values are the same. Let's go write down some of these points on our notes. Taking the data you got from your calculator, let's just rewrite at least a few of the points into your notes. Your table will have shown up with the value negative 7, negative 6, negative 5, negative 4, just to name a few points. And we have the corresponding y value of 5.5, 5, 4.5, and 4 for y1, and 5.3, 5, 4.7, and 4.3 for y2. We know the solution when we find the y1 values equal the y2 values. Therefore, our ordered pair is going to be the x value, which was -6, and the y value that was the same. And you'll notice that this is the same solution we got by graphing, so we have two methods that both will produce the same answer. Go ahead and give this example a try on your own. Once you solve both equations for y and graph them, you'll get the intersection point is at 2, -1. Systems of equations produce three different types of solutions. The first one is called an inconsistent solution. With inconsistent solutions, we're going to have no solution. And if we look at the graph to the right, we can tell why. We have parallel lines. Now, when we think about what that means in terms of the slope and your y-intercept, the slope of parallel lines is always the same, but the y-intercept has to be different. The second kind of solution is what we call an independent solution. Looking at the graphs on the right, we can see independent solutions always cross at one specific point. So we can say that we have one unique solution at the point of intersection. When we look at the slope and the y-intercept of these lines, we'll notice that the slope is always different, because only parallel lines have the same slope. But the y-intercept on the first graph, they have the same y-intercept. The second graph, they cross at two different places. So it could be the same, or it can be different. The last type of solution is what we call a dependent solution. And in dependent solutions, there is an infinite number of solutions. Looking at the graph on the right, we can see why. This one only has one line drawn. That's because the equations are all actually the same line. Therefore, if they're the same line, well, the slope will have to be the same. And the y-intercept also has to be the same on there. We can use what we just discovered about the three different types of systems to be able to classify systems without having to graph them. The first thing we're going to want to do is we're going to want to solve for y. Because once we solve for y, in step number 2, we can then compare the slope and the y-intercept based on the relationships we just saw above. On the first example, let's solve for y, divide everything by 8, and y will equal 1/2 x minus 3/2. Do the same thing with the top equation, 4y minus 2x equals 6. Add 2x to both sides, so 4y equals 2x plus 6. Divide everything by 4, and y equals 1/2 x plus, reduce that fraction, 3/2. Now we can compare the slopes. We have a slope of 1/2 and a slope of 1/2. If you look back at the three different systems, both inconsistent and dependent systems have the same slope. So now we have to go and look at the y-intercept, -3/2 and +3/2. Since they're different, this will tell us that we have parallel lines, which is considered an inconsistent system. We'll repeat the same steps on B. Divide everything by -3 to solve the bottom equation for y. So y will equal 2x minus 3. Then we're ready to compare our slopes again. We have a slope of 2x and a slope of 2x. Again, they could be inconsistent or they could be dependent. We'll go and consult the y-intercepts, -3 and -3. Since they are the same, we will say that this is a dependent system because they're actually the same line. Go ahead and give C a try on your own. Alright, here we have our two equations solved for y. The first one has a slope of -4, the second one a slope of -2/3. At this point, we don't even have to compare the y-intercept because they are different slopes, which tells us that this is an independent system. In everyday life, there's going to be times where we have to solve systems of equations. For example, the table below shows the population of New York and Los Angeles in the census report for 1950 to 2000. We want to know in what year will the population of both of these cities be equal. To find this, we'll use our graphing calculator along with a graphing tool such as Desmos. But first, we're going to divide our information up into what we call 3 different lists. Our first list will be the year, our second list will be the population of New York, and our third list, the population of Los Angeles. Then we want to redefine the years in some easier numbers to work with. Let's say 1950 is year 0. Then that means 1960 will be year 10, since it's 10 years after 1950. 1970 would then be 20, 80 would be 30, 90 would be 40, and 2000 is 50 years after. Now we have the information we need to go into our calculator. We'll start by pressing the Stat button, then Edit is selected, so we'll press Enter. Now we can put in all of our data into list number 1. We had 0, 10, 20, 30, 40, and 50. Then we can arrow over, and we'll put in our data for list 2. And make sure you press Enter after each addition. We'll arrow over again and do the same thing for list 3. Now that we have all of our data, we're going to press the Stat button again. We'll go over so Calculate is highlighted, and we'll select the 4th option that stands for Linear Regression. What it's going to do is it's going to take our data from list 1 and list 2, and it's going to give us the information for the equation of a line. We'll go down here to Calculate and press Enter, and we're going to need to write down the A value and the B value. Using the calculator to compare list 1 and list 2, it came up with the following values for A and for B. A was 0.15 and B was 12.93. We'll just round to 2 decimal places. And it told us on our calculator that y equals ax plus b. This is telling us what A and B represent. A is really our slope and B is the y-intercept. So we can plug these into our formula and say that y equals 0.15x plus 12.93. Here is our first equation we'll have to use in a minute. Then with step number 5, we are going to repeat this process using list 1 and list 3. We're going to repeat these steps now for list 1 and 3, so we'll press Stat again, go over to Calc, down to option 4, and this time we're going to change list 2 to list 3. So we'll press the second key, and then we're going to pick option number 3 to change it to list 3. Go down to Calculate, and here's the data that we need to write the second equation of the line. Using list 1 and 3 produces this result. A is equal to 0.25, and B is equal to 3.8. We'll plug this into our formula, and y is going to equal 0.25x plus 3.8. There is our second equation. Now we're ready for step number 6, which says we're going to graph both lines using Desmos, and then step 7, we'll find where they intersect. After I typed both equations into Desmos, this is what I got. I'm really only seeing one line, so I'm going to zoom out to see both of them. Then I'm going to look for where they intersect, and if you tap on it, this point will appear. Tap on the point, and that gives us our solution. So our intersection point is at 91.3 and 26.625. Now, since it's a real-world scenario, we need to interpret what these numbers actually mean. We were asked to find, in what year will the population of both cities be equal? Well, the population was our y value. That's what we were changing. This means that the population is going to be 26.6 million in the year 91.3. It sounds a little bit weird to say 91.3 is the year, and that's because it is. Remember that we said that year 0 at the beginning was the same thing as 1950. So we need to add 91.3 years to our starting point, which comes out to be 2041.3. We also don't talk about fractions of a year typically, so we can round this and say that in the year 2041, the population of New York and Los Angeles will be the same.